Okay, so 4.5 was rational functions, and then we're kind of shifting here to do polynomial and rational inequalities. So really what happens is a lot of the same stuff applies from our polynomial and rational sections. It's just now we are thinking about inequalities instead of equations. So we don't have equals, we have less than or equal to, greater than or equal to, and all that stuff. And instead of graphing on a Cartesian coordinate system for these, what we're going to do is we use our number line a little bit to give us some information, but that's really all we're going to do. We're going to solve them. We're going to find all this good information, and then what happens is we find a solution set, and interval notation is what we're going to get down to at the end of these problems. So, how do you go about solving polynomial inequalities? Well, first thing you want to do is move everything to one side so that you have an inequality that's in terms of 0. So you have f of x is less than 0, or f of x is greater than 0, or f of x is less than or equal to 0, or f of x is greater than or equal to 0. Even though in here it only shows the less than or the greater than, if it has that equals to aspect, it works the same way. Okay? So get everything moved over. And then what we're going to do is we're actually going to treat it like an equation. We're going to solve the equation of f of x equals 0. And those solutions that we get, those zeros that we get, are going to be boundary points. That's kind of a new term that you probably haven't played with yet. Boundary points. And so what we're going to do is we're going to then put those boundary points on our number line. Think old school number line. We're going to put the boundary points on there, and then we're going to pick some test points. Because what happens is when we put those boundary points on our number line, it splits our number line up to where we have this section, and this section, or however many sections we're going to have, and we're going to pick a point from each of those sections to test. And what happens is if we plug in a test point and we get positive out, we're going to put a little plus. And if we plug in a test point and we get a negative, we're going to put a little negative over our number line. And we're going to do that for every single section that we have. Because what that's going to tell us is it's going to tell us then which sections we need to be concerned about for our solution set. Because if we have a function that is less than 0, are we going to be concerned about the positive sections or the negative sections? If we have a function that has to be less than 0, do we want the sections that are positive outputs or negative outputs? Negative. And if we have a function that's greater than 0, then we're going to be concerned about the sections that have our positive outputs. Those are our intervals then. And so that's what happens. I think the procedure is great. It is the procedure you want to use. I think it's confusing until you see it worked out on a problem. So these are the steps. We have 4, 5 steps that we're going to take. A lot of times step 1 is already going to be done for you. You won't have to worry about it because they're going to give it to you as your function is less than or greater than 0. And here's what we're going to do. We're going to solve x squared minus 4x minus 5 is greater than 0. This is our first polynomial inequality. And step 1 is already done for us because everything's on the left-hand side. We have 0 on the right-hand side. We are good to go. Step 2 is where we change our inequality to an equation, and we're going to solve to find those boundary points. So we're going to have x squared minus 4x minus 5 equals 0. If we are solving this and it's a quadratic, you know lots of ways to do quadratics. I always recommend trying to factor first. Most of these are going to be nice factorable things. We need factors of 5 that are going to add or subtract, together to give me 4. Luckily, there's only one set of factors for 5, 1 and 5. We need more negatives than positives, so we're going to have minus 5 plus 1. So we find that x equals 5 and x equals a negative 1. And if we were solving our polynomial and it was an equation, we would be done. Those are our zeros. We're good to go. But this is an inequality, we're not done. These are our boundary points. So now what I'm going to do is I'm going to draw a number line. This is step 3. Draw a number line. I need -1 and 5 on there, so I'm going to go -3, 2, 1, 0, 1, 2, 3, 4, 5, 6. Like that. Make a number line. I'm going to stick x equals 5 on there. I'm going to stick x equals -1 on there. So I've plotted my boundary points on my number line. And when I did that, notice what happens. I have a section here to the left of that first boundary point. I have a section between my boundary points and a section to the right of my last boundary point. So I have 3 different sections. So that means I'm going to have 3 different test points. And you can pick any point you want that lies in any of these regions. It doesn't matter which one. I usually pick the smallest one available because it's usually the easiest one to compute. So for step 4, I'm going to find f of -2 because that lies here in this first section. What that means is I'm going to plug -2 into the function and see what I get out. It doesn't matter so much what I get out as if it's positive or negative. So -2 squared is 4. Minus 4 times -2 is a positive 8, minus 5, which equals a positive 7. So that means over here, I'm going to put a plus above my number line. That lets me know that if I plug in -3, I'm going to get a positive number as well. And if you don't believe me, put in -3 and test it. Put in -4, -10. All of those numbers should give you a positive number. Now between -1 and 5, I'm going to do 0. 0 is always the easiest one to do, so any section that has 0 in it, I'm going to use 0. Because that's 0 minus 5, which equals a -5. So this middle section is negative. And then f of 6 for the far right. 6 squared is 36. -4 times 6 is -24. And then minus 5. And it just so happens that once again I get 7. That's not always going to happen. Don't think that's always going to happen. It just happens this time. So I got a positive over here. So step 5 is where I write my interval for what my solution set should be. So I need to go up to the original problem where I had my polynomial is greater than 0. So which of those intervals am I concerned about? Am I concerned about the positive intervals or the negative intervals? The positive intervals. So I need to look at this first interval and say, okay, how do I write this interval as a interval notation? Okay, -infinity to -1. Now here's the question. Am I going to include that -1?
No.
Why not?
Because it's not like equals to.
That's exactly right. Our inequality is strictly greater than, and so since it's strictly greater than, we are going to not include our boundary points. If it was greater than or equal to or less than or equal to, then you include your boundary points. So not including the boundary point. I need to skip all of this stuff here in the middle because that's all negative, so I'm going to do a union. And then what's the remaining interval for my solution set? 5 to positive infinity. That's exactly right. Great job. So there's lots of steps, but none of the steps are necessarily hard, and all of them are actually things you've already been doing this whole semester. A lot of these are going to be solving quadratics or solving polynomials. We've done that a lot. Plugging in values, testing points, you've done that. writing interval notation. You've done that. So hopefully it's not super stressful because it's a lot of review of previous material. Let's do another one, though, before we add in our rationals, because rationals always make it more fun. This time we're going to solve x to the third minus x is greater than 0. Step 1's already done for us yet again because it's got everything by itself. So step 2 is where I set the polynomial equal to 0, and I find my boundary points by solving. X to the third minus x, both of those have an x term, giving me x squared minus 1. Now you can solve this multiple different ways. You can recognize that this is a difference of squares and factor it again. Or you can say, I don't know, I'm just going to set x squared minus 1 equal to 0, and you add the 1 in your square root, and you get plus or minus 1, and that's the other way that you could do it. Okay? So you could do it like this, where you have difference of squares, or you could say you have x, and then you have x squared minus 1 equals 0, x squared equals 1, x equals plus or minus 1. The risk of this way, using your square root principle, is that you'll forget the plus or minus. So I usually go with the difference of squares method, just because I don't forget then the plus or minus, because I've factored it. But either way, this time we are finding 3 boundary points. We found 0 is a boundary point, positive 1 is a boundary point, and negative 1 is a boundary point. So we're going to have more intervals on our number line than the previous problem. Zero, 1, 2, negative 1, negative 2. We have a 0 here, and there. So you can already tell we're going to have to do some fractional work here. Everybody's favorite, I know. But we have to pick a test point to the left of negative 1. Yeah, I always pick negative 2. And we're going to compute that. I have to pick a point between negative 1 and 0. I picked negative 1/2. Same thing for 0 to 1. I picked positive 1/2. And then 1 to infinity, I just picked 2. So if you find 3 boundary points, you're going to have 3 or 4 intervals. If you find 2 boundary points, you're going to have 3 intervals. So notice you have 1 more interval than you do boundary points. That tells you how many times you're going to test these numbers. So we would plug in negative 2 into the x to the third minus x. Do the algebra, you're going to get negative 6. Meaning that on this interval I have negatives. Negative 1/2, you would plug that in to x to the third minus x. You get a positive 3/8. Put in positive 1/2, you get a negative 3/8. Put in a positive 2, and you get a positive 6. So what would be my solution interval? Mm-hmm. So how do I write that in interval notation? Mm-hmm. And I used parentheses every time because we were strictly greater than. And Kelsey's right. We use the positive sections and not the negative sections because it said greater than 0. Good job. Are there questions on how we did our polynomial inequalities? Okay. Then let's think about rational inequalities. The nice thing is that they work pretty similarly. We're going to write the inequality as our function on one side and 0 on the other. We want to simplify it into one rational expression or quotient. So if we have like multiple fractions, we want to make sure we get them all together. So we have one fraction on the left is less than or greater than or less than or equal to or greater than or equal to 0. And then what we're going to do is we're going to set both the top and the bottom equal to 0. And any solution that we get out of those two equations are going to be our boundary points. And so we're going to get all of our boundary points. We stick those all on our line. If we choose our test values, we write our solution set. So not a whole lot different, except that we will have two different equations typically that we are playing around with, because when you have a rational expression, generally you have one equation on top, one equation on bottom, and so we'll have to split those and set them equal to 0. So not all that different. The only thing that we have to additionally be concerned about, though, is making sure that we do not include any of those quote-unquote trouble spots from our rational function. Because remember, with rational functions, what happens is anything that makes our denominator equal to 0 is a problem. And so when at the very end we write up our intervals, we need to make sure that our trouble spot or spots are not included in that interval, because if they are, we need to take them out. And we'll see that as we work through it. This first one plays really nice. So we have x to the third over x plus 6 is strictly less than 0. Step 1, again, is already done for us. Step 2 even is already done for us because we have one rational expression on the left. We just have one fraction, so it's already done. And so a lot of times with our rational functions, you get to skip all the way down to step 3. Step 3 is where we set our numerator equal to 0. That's the top. And we set our denominator equal to 0. And we're going to solve and find those boundary points. For 3x equals 0, that means x is 0. For x plus 6 equals 0, that means x is negative 6. So we have two boundary points in this case. So step 4, we make our number line. 7, 6, 5, 4, 3, 2, 1, 0, 1. Plot my boundary points at 0 and negative 6. So I'm going to have 3 test points then, because I have 3 sections. So I'm going to find f of negative 7, f of negative 1, f of positive 1. Again, you could pick totally different numbers as long as they lie in those intervals. There's nothing wrong with it. Negative 21 over negative 1, which gives me positive 21. Negative 3 over positive 5. Gives me negative 3 over 7. Positive. So I need the interval so that our rational function is less than 0. So which interval do I need? Yeah, I need the negatives. And in this case, it falls between -6 and 0. So my interval, it looks like an ordered pair, but it's not, is -6 to 0. Now, this is where I would need to make sure that I'm not accidentally including any of my trouble spots in my solution set. So I need to look at where does q of x, or the denominator, equal 0. Luckily, we already had to figure that out, and that's when x equals -6. But we've already excluded that point because we are strictly less than. So we don't have to take out an additional point. We've already taken out the trouble spot. So our final solution set is this -6 to 0, and it's good. This one played nice. We didn't have to worry about it. Had -6 been included, though, we would need to go one step further and take that out before we actually give the final solution. Does that make sense? Because we don't want any trouble spots. We don't want to divide by 0. We're not allowed to do that. Any questions on this one? One more. Solve x plus 1 all over 2x minus 4 is less than or equal to +1. It's a nice one to end on because this one requires us to do every step. It's not by itself yet, so we're going to subtract that 1 over, so that we have x plus 1 over 2x minus 4 minus 1 is less than or equal to 0. Now I got everything on the left. And if this was a polynomial function or inequality, we'd be done and we could move on. But for our rational inequalities, we want one rational expression on the left. So we need to combine these. We need to get a common denominator. So I'm going to have x plus 1 over 2x minus 4 minus 2x minus 4 over 2x minus 4. I changed the 1 into 2x minus 4 over 2x minus 4. So I can combine these all into one nice big rational inequality, so that I get a -x plus 5 all over 2x minus 4 is less than or equal to 0. And then this is the inequality we're going to play with. Because now that I have it written where there's one rational inequality, I'm going to split my numerator and my denominator so I can find my boundary points, to where I have -x plus 5 equals 0 and 2x minus 4 equals 0. And I'm going to figure out where those are 0 at. And if you want to, at this step, you could make a special notation for your denominator so that you know that this x equals 2 is your trouble spot, so that later on you don't have to do anything extra. You just make sure that you've excluded that from your solution interval. Okay, step 4. We need to plot these babies on a number line. Five and 2, so they're both positive. 0, 1, 2, 3, 4, 5, 6. Two, 5. So I'm going to have 3 test points. I need something to the left of 2, so I'm going to find f of 0. Something between 2 and 5, so I'm going to find f of 3, and something beyond 5, I'm going to find f of 6. F of 0, 0 plus 5 over 0 minus 4 is -5/4. F of 3, Negative 3 plus 5, or 6 minus 4, 2 over 2, which is positive 1. Negative 6 plus 5 over positive 12 minus 4, negative 1 over 8. Now, remember, our original, or what we worked down to, was negative x plus 5 all over 2x minus 4 is less than or equal to 0. So, for step 6, I need to find the interval that satisfies this inequality. So if I have to be strict or less than or equal to 0, am I worried about my negative sections or my positive section? Negative. So my first negative section goes from negative infinity to positive 2. And unlike all the other ones, this one is equals to. So I can include my boundary points. Skipping this middle section and going from 5 to positive infinity. Now the question becomes, are either of my trouble spots included in causing problems? Is my answer wrong in my notes? Where was our trouble spots? Yeah, just at 2. Is 2 included in our answer interval? Yeah, so we need to take it out. Because if we include 2, then we get 0 in the denominator and it causes a problem. So our actual solution interval will go from negative infinity to 2, but we're not going to include it. Because if we include it, we have a problem. Union 5 to infinity. So we had to take it out so that we didn't have any further issues with our function.